Alright, this video is going to be an explanation about how a basic tank circuit works, which is something that's confused me for a long time, because you really got to, have a fairly decent understanding of how a capacitor and an inductor really work, in various situations to actually appreciate it. So, making this for myself too, in case I ever forget, and I will. This is going to be at least 3 basic parts to this video. Okay, the first part, I'm going to describe what my setup is here and show you links to this circuit and stuff. And if I post this on YouTube, I may try to put some links in the in the description down below, but at the very least I'll actually show you the link too, so you can just kind of type a short link yourself without having to look at a description, just by looking at what I show you here on the video. But anyway, the first part, I'm going to describe how I have this simulator set up so you can understand what you're seeing here on these waveforms. It's really important you understand how this is connected to these wave shapes. Then the second part, and let me say this too, in between parts of the video, I'm going to flip over to this for like, a few seconds, probably like 10 or 20 seconds. So you can just scroll through the video if you don't want to hear these various parts. You can find the next part just by looking for this screen on the video as you, scrub through it. But anyway, the first part I will describe, what's going on with the simulator. The second part I'm going to discuss, basic capacitor, inductor theory, just real basic theory, just so you can see what the important concepts are behind understanding a tank circuit. Then the third part, I will actually go to the tank circuit itself and describe why things work the way they work in the context of what you've learned in the earlier parts of the video. So, but again, these individual segments are likely to be kind of long, especially as I describe the setup. So, anyway, having said that, well, here's the first intermission screen, if you will. Now, how I have this set up, okay, is pretty important to understand. First and foremost, you got to make sure you draw if you're doing this on your own, you got to make sure you draw these components right. It's very important that the simulator understands the direction you drew these so that they align properly. If not, what you're going to see is these things have 2 different voltages across each other, despite the fact they're in parallel. So you'll see 2 voltage waveforms, one for the capacitor and one for the inductor, that's 180 degrees out of phase. But that's not true. It's the current waveform that's 180 degrees out of phase, but the voltage waveform is identical because they're connected in parallel. So when you're drawing these components, you go up and look at passes, and you draw yourself a capacitor, or an inductor or whatnot, wherever the hell those are. Right there. That L key doesn't work apparently. Oh, maybe it will actually, because that might be a shift L since it's uppercase. Let me try that. That's a hard thing for me to push, but yeah. So shift L works. L makes a light or something, an LED. But anyway, yeah, when you're drawing that, I'll hit shift L again. Start from the top and move to the bottom, and then I'll hit just C, lowercase c. Do the same with the capacitor. Start from the top, move to the bottom. And of course you can start from the bottom, move to the top, but just do the same thing on both of them to make sure this thing thinks of the polarity being the same. So that's just a word of advice. Now down here, okay, you see a scope, and you can see the components light up, when I hit these various waveforms, right? So you can kind of see which one's associated with which component, but it's best to hover over the component itself and see everything turn blue down here. Okay, that means that's associated with a capacitor, and this is associated with the inductor. Although the thing is you're really looking at the current waveform and the current and voltage waveform here, but the voltage waveform is actually the same for both components because they are actually in phase with each other. So, and here, you can see as I hover my mouse cursor over this, this is telling me the voltage, and this is telling me the current, and then this is telling me the current of the capacitor. Alright, that's the current of the inductor, that's the current of the capacitor, and this is the voltage waveform for both. So that's how that's set up. And in this scope over here, I actually use this voltmeter here, which is on outputs and labels, and you go volt, scope, probe. Okay, that's what that is. So I drew that across here, and I'm measuring basically across this tank circuit. So you're seeing the actual voltage waveform for whatever's going on here. And these are all three screens I have here kind of set up in the exact same way, except this is, obviously for show and tell there. But again, the setup is still basically the same. Now, like I said here, you can see is the voltage across that probe. As you can see, it's highlighted over here. And here is the current. Okay, but I'm measuring the current right here, and how I have this orientated, you can swap terminals anytime you want, but this is proper orientation. I got this set up so that when it's measuring current, it's positive, because here's our DC voltage source here going through a switch, and when it has current going through it, it's flowing in this direction, because the inductor, once it's basically settled into its quiescent state, which is it's going to be its stable state. Once it's gone through its transient state, this is its stable condition. It has a bunch of current flowing through it. That current flows through here and to ground. All right, but here's where I'm measuring current. So I'm measuring current from positive to negative. Right. That's what's showing up on here. That's why it's a positive current. If I were to swap the terminals, it would actually be down here instead, and that's not what we're wanting. So I'm wanting to keep this, again, in such a way where, it's kind of what you would expect if you set this up on a test bench, sort of, because in theory you could set this up on a test bench. This would be your ammeter. Again, your positive red terminal would be here, your black terminal would be there, and here's a separate voltmeter, with the positive red terminal there and the black terminal there. So, anyway, that basically describes how this thing is set up. I don't think I'm leaving anything out, but it's important to know. And I selected the component values on here just arbitrarily, because you could use different values if you want. I was thinking about using, like 1 Henry and 1 farad, but these are actually, especially on the capacitor, a more practical value because that's still a pretty damn big capacitor. That's like 10,000 microfarads. It's not tiny, but it's not huge. But anyway, I stuck with these values because you can see here's the frequency reading, about 15 hertz. So that's not super high frequency, but not a super low frequency. So it's just kind of a more practical value. But on your bench, you could, if you find an old like transformer or something, it's likely to have a multiple, several Henry inductance. But if you wanted something like this, you could actually use an actual inductor, which may have better, more linear profiles, because real components aren't going to behave, like these ideal components. The ideal components are good to give you a basic understanding of what the hell's going on. Anyway, let me do an intermission screen, and then we'll start talking about component theory. probably should put elevator music or something in on these intermissions. I just want to make sure you can scroll through it to see it. Okay, but enough of that. Okay, now there's a couple of, several important principles to understand about capacitors and inductors. I'll illustrate here, starting with a capacitor. I'm going to show you, again, really fundamental textbook, and a lot of you guys probably already know this stuff, because again, I've known most of these things for years, but just being able to connect the dots as to how these dynamically interact, that was the tricky bit. But you've really got to especially understand inductors. So we'll start with capacitors because they're easy to understand. I basically reset the simulator. I will hit run, because the switch is open, so there's no current flowing or anything like that. Notice I have a 1 ohm resistor, and here I have a 1 ohm and a 10 ohm resistor. I'm probably not going to use a 10 ohm resistor for this, but I'm going to use it to demonstrate an important point in inductance. Okay, but let me go ahead and close the switch. Alright, and you can see what's happening. At the very first, we've got a very high current, 9, 10, it's really 10 amps. I'll speed it up here so you can move it along, and I'll slow it down to 0. But see right here, you can see the current flowing through it. It's like 10 amps, because that's what happens with a capacitor. The moment you hook a source across it, its current will be the max, and it'll never be as high as that again throughout its charging cycle. But since it has no voltage across it, basically the voltage 100% gets dropped across this resistor, and it starts at 0 volts across the capacitor, is what you're seeing here. It's at 0 volts here, but then the voltage starts increasing, but the current starts falling. So the voltage is increasing while the current is falling. That's a very important concept to understand. And eventually, when the thing is fully charged, the current is 0, but the voltage is 100%. You can see the little dots there aren't moving that fast, because the capacitor is almost fully charged. And so you'll know it'll take 5 RC time constants, to charge up. So, but I'm not going to go into that. That's textbook stuff. It's not important for what I'm going to discuss in this video. Okay. Now that I've got it fully charged up, I will put a resistor here, okay, and disconnect the switch. Now I could do this live, but that'll create like hiccups and stuff if I don't slow it down or stop it, but I prefer to slow it down. Now let's pick up, and I'll show you what happens here. Okay, now you can see right here the current is negative now, but what that means is the capacitor is discharging, because the current has instantly gone very high negative, and again it's going to be, the current is not going to be this high ever again. It's going to diminish from that 10 amps that it's basically starting at, okay, and fall to 0 amps. And more importantly, the voltage is starting at 9 volt or 10 volts really, and then falling down to 0 volts. So basically the voltage is falling as the current is also actually decreasing. It's a high negative value, but that's because the capacitor is discharging. But the point is, it's a large negative current now because basically the capacitor is discharging. So you got current flowing in this direction now, and at first it was flowing in this direction, right? Before I put the resistor in it, but now that I disconnected the switch and put that, current is actually flowing in the opposite direction. Now that's why it's negative here and positive here. So but you can see right here, when we were just starting out, you've got a high positive current, and the voltage is increasing as the current drops. because it's charging. But here you get a high negative current, which is decreasing as the voltage is also decreasing. So, those are, going to be fairly important, to understand. The important thing to remember is that, when the capacitor is at 0, you apply a voltage across it. That's when its current's going to be max, but the voltage across the capacitor will be slowly increasing as that current falls. But then when it goes into discharge phase, well, something similar but a little different happens. You get an initial negative current spike, okay, in this case, and as that current falls off towards 0, your voltage also falls off to 0. So now what might confuse you a little bit later is the fact that this whole waveform set will reverse in this, because this will generate an AC waveform. This tank circuit will be an AC wave. This is still just a DC response. So even though you got currents flowing in the opposite direction, this is still a DC circuit, not an AC circuit. So a tank circuit like this will start, like this will start off as a DC circuit, and in my setup here it will. But once you disconnect that switch, it'll turn into an AC circuit. So you'll see the roles basically flip here, just as if I changed this voltage from positive to negative, to a positive 10 volt source to a negative 10 volt source. Then you would see these waveforms flip, but it's the same concept. But you got to, and like I said, I'm going to try to keep things in the concept of in the context that I have here as I try to explain this when we get to the tank circuit. But we'll cross that bridge when we get to it. At any rate, that shows you basically the basics of a capacitor. And most, AC/DC people have gone through an AC/DC course or whatever. This is like 101 kind of stuff. But I wanted to review it to point out a couple of important concepts that, about capacitors, that will, be important later. But it's namely that when you first apply a voltage to a capacitor, its current is maximum, and it falls off from there. It'll never be as high, like in this example, as this 10 amps ever again until, the thing is, well, forever, until you change the state of the switch. It's never going to be more than 10 amps. It's a decreasing current. And the same here, when you flip it over to discharge phase, it'll continuously decrease towards 0, from a negative value until it hits, until it's fully discharged. But see here, basically you've got an external source of power. That's what's causing it to charge. And here, well, it's the source of power that's discharging through a load. So, that's why, in this case, there's an external source, or 10 volts, applied through the switch is what's charging the capacitor. Here, the capacitor itself is actually the source of power because the switch has been disconnected. So the only direction current can flow is around in a circle here. But at first, the current is flowing through here, as you saw when I didn't have this resistor on. And God damn it. I disconnect this because if I didn't disconnect this, it would only charge to half that voltage. So I don't want to do that. So that's why I charge it up with just this, so it'll charge up to the full 10 volts. If I didn't, it would only charge up to 5 volts because I would have a resistive voltage divider here. But that's why I keep removing these components like this, because I'm trying to give you as pristine, of a demonstration here as I can. And by the way, if you wanted to, if you wanted to, see the link to this, I can create a short URL. Oh hell. now you're gonna. But anyway, I'll create a short URL, and yeah, then you can just type this in, or like I said, I'll probably try to paste a link to it. Let me go ahead and save it. I'll have to stop the video while I'm doing that, so you don't think it's an intermission. Okay. But yeah, so that's how capacitors work. For the sake of this discussion, now let's move along and look at an inductor individually. Okay, and I'm going to have to do the same thing, and this is even trickier to do with inductors than capacitors. Alright, so let me go ahead and run the simulation, but I'll reset it. Alright, I go ahead and flip the switch. Alright, let's get it moving along here. Okay, that's good enough. Okay, so right here, you see that the moment I flip the switch, there was 0 voltage across the inductor before I flipped the switch. You can see the direction of the current flow here, and you can also see that it's like at 9.9, essentially 10 amps. This is not fully up to charge yet, but so here in orange, you can see what the current is, but you can see that the voltage starts out at 10 volts instantly. I mean, instantly there was 10 volts across the inductor, but there's also 0 current at the same time. That's because inductors resist. Inductors do not like to have sudden changes in current, so they try to resist that, and they do that by generating a voltage across them that opposes the voltage that you're applying. So an inductor starts out with high voltage, across it the moment you apply voltage. It's like instantaneous. But the current starts out at 0, but as the inductor, the inductor's current charges up, because when an inductor has current flowing through it, that's when it actually is storing energy in its magnetic field. So what we see here is a time constant, like 5 time constants here, as it tries to store energy in its magnetic field. And the interesting thing too about inductors is that the time constant, it's RC, R times C for the resistor capacitor time constant, but it's L divided by R, for the inductor time constant. So what that means is if I were to put this resistor in here instead of this 1 ohm resistor, believe it or not, it would take less time with a bigger resistor for the inductor to charge up its field. Now, what would that be, you might ask? Well, you got to understand something. If you use a bigger resistor, see, right now we got 1 ohm, right? And we got 10 amps flowing through this thing, essentially. Well, okay, that's a lot of current to be flowing through an inductor. But if I put a 10 ohm resistor in there, it would only get to 1 amp, not 10 amps, with our 10 volt source. So it would do that faster because it's not having to supply as much current through it. So that means it's storing 1/10. It has 1/10 of strong of a field, basically. So instead of it being a 10 amp field, it's a 1 amp field. So it's having to store less energy. Again, remember, it's 1/2 Li squared. So it's like it'd be like 1/100th the energy that it's storing right now. So because of that, it's a lot faster because it's having to store less energy in its field. So that's why it's faster with a bigger resistor. But with a smaller resistor, it's slower. In fact, if you remove this resistor, it'll have a certain natural charge rate to it. But the thing is, if you put a voltage source across just an ideal inductor, its current will increase forever, but it will actually increase at a fixed rate. But anyway, that's still not important for what I'm going to go into in this video. It's just something to look into if you're interested about it. Some unusual things that you wouldn't expect. You wouldn't expect a big resistor to make this time constant shorter. You'd expect it to be longer based on the capacitor, but it works just the opposite. So, and again, it's this duality between capacitors and inductors that causes a lot of this stuff. And that's why it's important to have an intuitive understanding of some of these things. But at any rate, right now we have, because again, with an inductor, we've got a fully charged up field. Its current is sitting here at 10 amps with 0 volts across it. Because again, an inductor will start, when we first close the switch, it'll start with a voltage across it equal to the source we're applying, as of this point here. So, but, in this case, again, it'll see 10 volts across it initially, and 0 current flowing through it. That's why you see initially 10 volts across it, but at 0 amps. But as the current increases, up to 10 amps, the voltage is decreasing. And I have these set at 2 different scales. You can see that I'm at like 10 volts of division on the voltage, but it's like 5 amps per division on the current. So, but I'm doing this for a very specific reason, and you'll see that here they're more equal, okay, on this graph, but here I have these set at different scales, and you'll see why in a minute. But at any rate, so we got this thing fully charged now. Let's see what happens when I flip it. Now it's important when I turn the switch off to put the resistor in, to connect the resistor up before you open the switch, because this simulator, if I open the switch first, it'll just dump all the energy will just instantly disappear there. So you don't want to do that. So connect your resistor, then flip the switch when you're doing this experiment. It's very important. Okay. Alright, so you can see that there's flow there. The flow direction has, is still, because what the inductor is doing is, like I said, inductors don't like current to change going through them. So they'll put whatever voltage across themselves they need to try to maintain that current. Now let's see what the ramification of that is. Oh, looky there. The voltage is gone negative all of a sudden. That's interesting, and the current is falling off at that same period. So basically it generates a negative voltage on it, so it can try to maintain the direction of current flow. So, but like I said, we got current flowing down in a loop, but in order for it to maintain this direction, well, instead of it being positive there and negative there, as our original voltage was plus and minus when I had the switch closed, well, now that I opened it, well, now it's plus and minus this way. So it's actually, the inductor is acting like a source of current now, not a sink of current. So it has to flip its direction because it wants to keep its current constant, so it can flow around this loop. So it had to flip its sign to do that. And you see that instantly the voltage flips. And I mean, it's like instant. It just, I don't know how the speed of light factors into this, but I mean, it's like an instant thing. It's almost like magic, how its voltage flips around. But you can see that its current, is decreasing now as its voltage is decreasing, whereas here, its current is increasing while its voltage is decreasing. So, anytime there's a change in state, this is going from charge cycle to discharge cycle. So anytime there's a change in state, the voltage always starts out at maximum, current at 0. Maximum, here current at 100%, but it's trying to maintain it at 100%. But we're in the discharge cycle, so that's why you got decreasing current here and increasing current here. But the voltage is always flipped. And the capacitor, you remember, during the charge cycle, well, the current started out at 100% and the voltage was at 0, so the voltage slowly increased as the current decreased in a capacitor. And when you go into discharge, the voltage is slowly decreasing, from a positive level as the current, starts decreasing. It starts at 100% and starts decreasing as the voltage also decreases during discharge. So, but if you'll notice, here the current, since this is a DC circuit still, the current is always positive, alright, but the voltage is flipped. Now in the capacitive example, which I kind of wish I would have left that up here now, but you'll see, that the voltage is always positive, alright, but the current flips. So again, you have this kind of inverse behavior between capacitors and inductors that it's sort of important to have an intuitive understanding here, and that's why you're not going to see much math in here at all. I'm just trying to give you an intuitive understanding of what's going on with this so you can understand a tank circuit later. And just like I said with inductors, if I were to flip this to a negative voltage source, all these waveforms would reverse, because again, this is DC right now, but when we get to a tank circuit, it'll be an AC situation that you'll see take place, because this is basically a way of converting, kind of a lame way. You wouldn't want to do this in practice, I don't think, but it's a way of taking a DC signal and turning it into an AC signal, kind of in a loose kind of sense. Again, I don't know if you really want to do that in practice or not, but I mean, I don't know that it would have much utility to it, because again, these waveforms die out. But that's another topic altogether. Okay, but I think that probably will wrap it up for this. I may come back to this a little bit, when we get into the next section of the video, but I think that still does it for this general section, so let's go ahead and do an intermission. But yeah, this next section we'll discuss the actual tank circuit now. So alright, so intermission over. Hope we got your popcorn and your snacks. Now this is we're going to start talking about the tank circuit itself now that we discussed capacitors and inductors and how they behave individually. Now let's see, you can see, I'm trying to think if I want to keep these. Hold on. Alright, so what I want to do at first is well, let me go ahead and at the very first, let's take care of the URL business. Okay, so here is a basic link. And I'll create a short version of it, and if I remember to do it, I'll paste it in the description. These two circuits are basically the same, so you can just use that one, because you're not going to get this waveform. You'll just have to redo it yourself. Let's see. This one I'm trying to keep this way because it's actually easy. It's why I don't really want to run a simulation on it, because it's this is just kind of a quirk of Fallstat. I got lucky and it made the voltage waveform larger than the two current waveforms, so it's easier to identify it. Whereas this other one, you see everything's kind of the same magnitude, so down in this plot anyway. So anyway, but let me go ahead and just reset this SOB and I'll run the simulation. Alright, so we're at zero state, there's no energy in the system. Now when I close the switch, see what's happening. It's going through its transient phase, where it's trying to stabilize to its, quiescent value. Now, let me slow that down. So you can see what's going on here. Basically, the capacitor has no voltage across it at this point, and the inductance, though, has maximum 10 amp current flowing through it at this point. Okay, that's in its stable state. That's what you see right over here. So there's no voltage across the tank circuit, because this is an LC tank. That's what they call this. A capacitor and an inductor in parallel, is a tank circuit. But it has a natural tendency to oscillate, even though it does act like a filter too. If you actually get into the rest of electronics, this actually acts, this is what you call the condition of maximum impedance. So it's an ideal components, it'll be infinite impedance, if you actually had a frequency flowing through this at the natural resonant frequency of these two components, which is mathematically it's 1 over 2 pi radical LC, is the resonant frequency. But we're not going to go into that. But that is what determines the frequency of this tank circuit, because it actually oscillates at that resonant frequency. But if you use it as a filter, it'll actually tend to block that frequency. So if you had a 15 hertz signal going through it, which is what this will end up being. If you have a 15 hertz signal going through it, it'll block that, but it'll allow frequencies less than that to pass. Like, for example, like a 1 hertz frequency would mostly pass through the inductor, because at 1 hertz the inductor will act like almost just a piece of wire. It'll have very low amounts of voltage across it. In fact, it'll allow DC to pass, like you see here, with 0 volts across it. The capacitor will block DC. Okay, that's why it doesn't have any current flowing through. You can see the little current dots aren't moving at all here. So it'll block DC, but it'll allow really high frequencies. So if you had like 30 hertz, let alone 300 or 3000 hertz flowing through it, the voltage across the capacitor, would actually be increasingly small. Okay, so but across the inductors don't like high frequencies, so the voltage across its resistance, what they call reactance, would actually increase, whereas the reactance of the capacitor decreases. But again, I'm not really going to go into complex number theory and impedances and reactances and stuff like that. That's actually not important really to understand intuitively what's going on with the tank circuit. And that's, if you want to know the rest of it, go study AC/DC books, or find some stuff online. It's just a different topic that I'm not going to discuss in this video series, or this, the length of this video, this series of parts. Okay, but basically you see what's going on here. This is the quiescent state. The switch is still closed, and here this orange curve is our current, and it stabilizes at 10 amps, and the voltage, as you're seeing it here, is 0, right? And the current is 10 amps even on this setup. Because remember, down here, this is just looking at the actual current and voltage from the components themselves, and that's what I said. I actually selected these components to say, view in new scope, or view in existing scope. So, that's where this data comes from. Whereas this data, as I said in the first part of the video, comes from this meter here, and then this little current probe here. So, but this is directly what's going on in the components themselves. That's why drawing them properly is important, like I discussed in the first part of the video. But the quiescent state is that you end up with a current constantly flowing through the inductor, which is what maintains the energy it has stored in its magnetic field. And it's got that energy stored in its field because it's got a current going through it, and it's an inductor. Alright, and it's got zero voltage. That's how you know an inductor is charged, that its voltage is zero, but its current is at max. That means the field is fully charged. Now, conversely, a capacitor is discharged because its voltage is zero, and there's no current flowing through it. So, it's basically, it might as well just be sitting off in your toolbox somewhere, in its current state of affairs, it's not doing anything. But at first it does. See right here, I'll show you, that's the capacitive current and voltage waveforms, alright? That's the inductive current and voltage waveforms. So, and again, this voltage is common to both of them, but here's the inductive, or the capacitive current curve, here's the inductive current curve. And like I said before, the inductor, is charging up, as its current increases, whereas a capacitor, is basically, it starts out with super high current across it, because at first it is actually receiving some current, because it does initially have impressed voltage across it. You see the voltage isn't zero, and it's not 100%, but when it's in this intermediate state, the capacitor is actually charging up at first. And that's what you see. At first it's got a really high current, but it's almost 10 amps. Okay, but it's decreasing as the voltage across the capacitor increases. And when its current hits zero, which is right about here, that's at peak voltage. But that's not just the voltage across the capacitor, it's also the voltage across the inductor. But you can see the inductor is not fully charged yet because its current hasn't hit peak. So the inductor is still charging, but that did allow for a little bit of a voltage, to be set up across the capacitor. Because remember, the inductor's current starts out at zero and is slowly increasing. But right now, the capacitor's getting in on some of that action too and charging itself up, and it's reached peak charge here, which interestingly enough, is about 5.4 volts or whatever that's set at. So about 5.5 volts or so, because at that point the inductor is starting to chime in, and that's why the current flips on the capacitor and goes to a discharge state. So here, the current in the capacitor's gone negative now, and it starts at zero because it's starting to feed its energy off into that inductor now. So, and you can see its current peaks down around here just before the inductor is fully charged, but the voltage across the across the tank circuit is starting to drop, and eventually that hits zero, right? It hits zero right about here, about when this current peaks. And this voltage is this current is like 11.6 amps, which is higher than you'd think. But that's, because that 10-volt source up there can only really supply 10 amps to it. But this extra, 1.5 amps is actually coming from the capacitor. So that's why you have a higher than you would expect current here, because that's the capacitor basically discharging into the inductor at the same time. As everything heads to quiescence. Now you start to see a little bit of an oscillation here, because the voltage actually goes negative for a little while as that inductor is dropping some excess charge in it, trying to get its current level down to 10 amps, which is, what it's naturally going to be, but it's basically just trying to get rid of the extra power from the capacitor. Because again, it should be at 10 amps, and that's why it'll stay, as long as I have that switch closed, it'll stay at 10 amps forever and 0 volts forever. That becomes its natural state. Now, if I used like a bigger resistor value here, you would actually see a lot more oscillations in this. It takes like 4 or 5 seconds. If I put a 10 ohm resistor in there, which is what I originally started with in this thing, it takes like 4 or 5 seconds for this to stabilize at 0 volts. So even right here, it's not exactly at 0 volts. It's still oscillating a little bit, but it dampens really quick. So, that's why I use the values I use, just to give quick results so we don't have to get too confused, and you can kind of see everything on the same screen a little bit too. But at any rate, this basically is the stable state of the circuit. So, you know, at this point, you know, I'm going to go ahead and open up the switch and you can kind of see what happens. Let me pick up the simulator speed here. Alright, so we've gone from our quiescent state, and so that's why I wanted this to damp fast so you can actually see the quiescent state at the same time you can see the operational state. So this was, you know, when I first flipped the switch, you know, so you can see the current in the inductor, you know, is all happy, you know, humming along, and then all of a sudden now it's starting to decrease, you know. So in other words, I removed, I had to go turn off that stupid beeper, so I forgot what I was saying. But basically, like I said, you know, at the very instant, you know, we flip that current, you know, you see that the capacitor, you know, because this is the current through the capacitor, you can see it highlighted there. You know, actually starts out like you would expect in a way, because now it has this high current source from the inductor, you know, feeding it basically. You can see the direction of the current, you know, where it stands right now anyway. But basically the direction of the current at the get-go, you know, is actually negative from the capacitor, but it's positive from an inductor. Okay, the inductor has all the energy in it at the moment, because remember, over here, just before I flip that switch, the capacitor has no energy in it at all. The inductor has 100% of its energy in it. But now, what's happening is the inductor is losing energy. And remember, these components, they're ideal components, and reactive components like capacitors and inductors don't, you know, they don't consume energy. So, you know, real components, that's a different story. I mean, you'll see some internal resistances associated with capacitors, like leakage resistance and equivalent series resistance, and inductors always, you know, have resistance associated with the wire they're wound on, plus they can have magnetic losses and a bunch of other bullshit, you know, that if you get really into it, you know, you'll see. But again, that's not what this video is about. This video is about understanding the basic concept of this energy exchange and how it works, because it's non-intuitive, you know, if you don't understand how these components work. But what's happening here is, like I said, we get all this energy stored in the inductor, okay. And oh shit, you know, there's something I meant to tell you earlier that I gotta point out. Hold on, let me stop the. I mean, basically got this stalled. I don't think there'll be a problem leaving it running. Yeah, I meant to go into this. Let me reset the simulation. That's why I had that 10 ohm resistor. I forgot to go into that earlier. Okay. Now here we have a default state, right? Now let me remove this resistor, and then let me charge up the inductor real quick, because this is a very important thing I left out in the theory earlier. Okay. Alright, so, you know, I popped that to 0, and I showed you what happened when I put, you know, we got 1 ohm charging the inductor and 1 ohm discharging it. You know, you saw that the voltage flipped. I mean, it was like 10 volts here, and then it became negative 10 volts on the other side as the inductor current was discharging. Well, let me show you what happens when you put a larger resistor. Remember, I talked earlier, and notice how I did that. I put the resistor in first, then opened the switch. You know, you can see what's happening with the current dots here. But earlier, you know, I said, you know, I was talking about the charge constants, you know, and how a bigger resistor leads to a shorter charge time, but a smaller resistor leads to a larger charge time because you put more energy in the inductor. That's why it takes longer for a small resistor to charge an inductor than a large resistor, because you're storing more energy in the inductor, but it can only, because of its current limit, which is based on its inductance, the rate of current increase is directly, proportional to the actual inductance in henries. But for a given inductor, a small resistor takes longer for this field to charge than a bigger one, because you're putting more energy into the inductor. But here, if you discharge through the same size resistor, the voltage it generates is equal. But if you put a bigger resistor in it, you're going to get 10 times the voltage out of it. And you'll see that here in a second. Alright, that's why I have these at two different scales. That's why I set this scale up over here like I did, because you could see how the scale of this graph changed. Now all of a sudden this little voltage thing here looks small, but it's still at 10 volts, because that's what we charged it up at. But now it's like, you won't see it, but it's, you only see negative 64 volts because it goes off the graph. So, but it's like 10 volts per division, so this is like 40 volts you can see there, but it's going to be about a 100 volt spike. But you can also see the amount of time it took the inductor to discharge was really quick. I mean, it's like 1/10 the time it took it to charge to begin with. So it generates a much higher voltage, but because of the fact it's got a higher voltage, the time it takes it to discharge is really short. But remember, the whole time it's trying to keep that current at 9 amps, just to be about 10 amps to begin with. The moment I flip that switch and put that resistor in there, it's trying to maintain that at 10 amps. But since it's a 10 ohm resistor, because see, if it was a 1 ohm resistor, it would only have, that 10 amps of current it had flowing through it would generate 10 volts across a 1 ohm resistor. And it would take the same amount of time to discharge as it took to charge. But because I put a 10 ohm resistor in there now, well, that's 10 times the resistance I charged it with. This inductor has 10 times the magnetic field that it would have if I charged it with a 10 ohm resistor. But as a result, that'll increase its current. If you know anything about inductance, and the voltage by Faraday's law, that the voltage equals the derivative, the d/dt over times the inductance. Okay, that's the voltage it's going to generate. Well, because of that basic concept, you put 10 ohms with 10 amps going through it. Because remember, this is 10 amps to begin with. Well, we put a 10 ohm resistor in there, so that's going to generate 100 volts. But because it's generating 100 volts, it will dissipate, it will get rid of that energy really quick. And that's what happens, so this resistor basically is absorbing all that energy, but because it's 10 times as large, it absorbs energy at 10 times that rate. It's got 100 volts across it and 10 amps going through it. But since it's 10 ohms instead of 1 ohms, it's able to eat that energy up 10 times as fast. So basically, that's what happens here. You get a huge voltage spike out of it, but the current, it tries to maintain it at 10 amps, but it can't, because it's running out of energy, basically. It tries to maintain it at 10 amps, but it can't. And it does that by generating a high voltage, because it's trying to maintain that 10 amp current. And because this resistor is 10 times as big, it generates 10 times the voltage. Again, like by magic, it generates 10 times the voltage to try to maintain that current flow. But it can't do it. It runs out of energy a lot faster because it's generating that higher voltage into that 10 times the resistance. So this resistor, again, in fact, it's got 10 times the resistance, can absorb energy at 10 times the rate of this resistor. So because of that, this eats that resistor up. This bigger resistor, eats that energy up like a sponge compared to a 1 ohm resistor. So basically, and plus, by the way, too, if I had used like a tenth of an ohm resistor, a 0.1 ohm resistor, it would have taken this 10 times longer to discharge, and would only have generated, instead of 10 volts across it, it only would have generated 1 volt across it. So it would take it like 10 times longer to discharge. So it works the opposite way too. But it's more interesting if you're interested in high voltages. This is a way of generating high voltage. But it's going to be much briefer than how you charged it. But basically, the more current you put into it, and then the more current you charge through it. If I'd used a 0.1 ohm resistor here, I'd get 100 amp charging current. Instead of just this curve right here being 10 amps, it'd be 100 amps. Okay, and then when I switched in 10 ohms, well, that would be 1,000 volts. Okay, because it would generate 1 kilovolt trying to maintain 100 amp current through a 10 ohm resistor. Now, of course, there are practical limits, and you may be thinking, well, yeah, it'd probably fry your resistor, and it might, depending on how much energy you store in it. But remember, it is very brief. So the power rating of the resistor isn't as big of a factor as rather a current. Your inductor can handle the current, and plus, can it handle the voltage? So if you wanted to generate like if I put, 100 ohm resistor here, for example, it would generate 1,000 volt spike instead of 100 volt spike. And if I were to put a 1K resistor here, that's 1,000 times that. So, it generate 10,000, volts across it. The problem is your resistor may not be able, a real resistor may not be able to handle 10,000 volts. Believe it or not, resistors have voltage ratings on them, and typically they're only 200-300 volts if you're lucky. You've got to buy special resistors to get, like high voltage, and it boggles the mind, but believe me, it's true. You will blow out resistors if you try to put, and not blow them out as in blow them up necessarily, but I mean, if you put high voltage through a regular resistor, it'll arc over it and destroy it. Again, even if it's low current, high voltage, like from a flyback transformer on TV, you can burn out a standard resistor, and its resistance will basically be zero afterwards. I've even blown out some fairly high voltage resistors that way. Not using this, but I mean like flyback transformers and stuff like that. But resistors do have voltage limits on them. They do, and you've got to buy special high voltage resistors, like from Mauser or DigiKey or somebody like that. They're not too terribly expensive, but I mean, still, you got to think about that. But again, also you'll have trouble with your inductor. I mean, if you got to make sure your inductor is going to handle like 10,000 volts, okay? Because there's a good chance that it's, you'll have arcs between its windings, and that'll, basically damage or destroy the inductor. So at any rate, and then not to mention, too, there is such a thing as the capacitance between windings of an inductor too. That may be a problem there too, a little bit. But at any rate, I'm just saying, it's interesting. You can generate high voltage, but the practicality of it, is a little more dubious. But you can certainly generate higher voltages than you might expect, using this concept here. But at any rate, I forgot to mention that earlier. But back to this, because that's a real important little concept that I was just talking about over there. But like I said, and we'll get to that in a second. But at any rate, right when you flip this switch, we go from from it generating 10 amps to all of a sudden, and being just happy, it's just sitting there, it'll stay there forever. All of a sudden I flip the switch, and well, the current through the capacitor all of a sudden jumps to maximum, again, as you would expect a capacitor to do when you're first applying a voltage across it. And you can see what the voltage across being applied to the capacitor is. It's coming from the inductor. It's coming from the current, basically, across. The inductor has 0 volts across it, right? Because it's sitting there happy and everything. But boy, once you start, that inductor starts discharging, because we've taken it off the charging circuit, it starts discharging into the capacitor. Okay, the inductor is sitting there at 10 amps. It wants to, it'll do whatever it takes to maintain this 10 amp current. But of course it can. It's got a limited amount of energy, but it does its best to maintain that 10 amp current. But again, since a capacitor, when it's first starting to charge, has its maximum current, and again, it'll never be that high again, but we're not just talking about DC anymore. This is actually now an AC circuit. Just bear that in mind. But what you see here is you see this negative spike. Well, that means, that basically the capacitor at this point, and ignore this because, again, remember these dots, this is what's going on right here, not where I'm talking about here, so ignore the dots for right now. But this negative sign means that the current, is the capacitor is charging, and the inductor is discharging. Remember, it's the sole source of current, and it wants that current to be flowing in that same direction no matter what. Okay, so basically it's discharging into that capacitor. So the capacitor's voltage is starting at 0, but it slowly starts increasing, as that inductor, is discharging its current into the capacitor. But as the capacitor charges, its current begins to fall, okay, as its voltage increases. So basically, that continues. You see what the current in the inductor is doing. It's ever falling, and the current in the capacitor is also falling. But remember, the voltage is increasing. Now, remember what the definitions I said earlier are. Well, when an inductor, when its current is falling, it's in a discharge phase. So, because again, capacitors are all about voltage, inductors are all about current. So, but when an inductor is discharging, okay, its current is falling. Alright, but when an inductor is discharging, like I was talking about just a few minutes ago, with the 10 ohm versus 1 ohm resistor and everything, that inductor will generate whatever voltage it has to try to maintain that current. It was started out at 10 amps and is trying to maintain that 10 amp. The moment I disconnected that source, it wants to keep that flowing, and whether I put a 1 ohm or 10 ohm or 100 ohm resistor in there, it'll generate whatever voltage it needs to try to maintain that current level. That's what it does. That's why if you have an inductive load and you open up a toggle switch, it'll arc the switch. In fact, your switches aren't ready to handle those arcs, it eventually eat up your switch. Those inductive spikes, that's where it comes from. It'll generate whatever voltage it needs to try to maintain whatever current's flowing through that circuit before the switch is open. And if that means it needs to create a 10,000 volt arc, it'll create a 10,000 volt arc. So you got to remember that. Those can be serious issues, when it comes to practical real world, electrical circuits and systems. But basically, so what's happening here, is again, you've got a capacitor that's charging, and just like a capacitor, it's when it's got zero energy into it, it'll always start out, again, when it's in its charging phase, it'll always start out with really high currents, and then, as it will when it's in its discharge phase, again, it's always super high currents when it's charging and when it's discharging. But the difference is, its voltage is increasing when it's charging, whereas it's decreasing when it's discharging. So what you see here is a situation where it had 0 volts and 10 amps going through our inductor, but 0 volts across the inductor and capacitor. All of a sudden I flip the switch, now the current shoots way the hell up through the capacitor to the same magnitude as the inductor is supplying. Because basically this is telling you that you got 10 amps in the inductor and 10 amps in the capacitor, but the current directions are opposite. So here, this, it's got a positive current flow, which it was trying to maintain, like it was over here. It's positive current flow. It's trying to maintain that positive current flow, but the only place for it to go now is in that capacitor, since I opened the switch. So basically that current is flowing into the capacitor, which is fine. Capacitors love that, because if they have zero energy in them, well, guess what? That's when they want maximum current. So that's also why I tried using the same value for both of these, so it's less confusing. So if I did like 100 millihenry millifarad here, I'd want 100 millihenry here, just so these things are all equal magnitude. But basically that's why you got equal current here on both sides, but you would have that no matter what, because remember, regardless of the size capacitor we had here, since we had 10 amps flowing through our inductor, it would make 10 amps flow through the capacitor, whatever voltage it had to generate to do that. So that's a different subject for right now. But right now, hey, that capacitor is happy with 10 amps and it's charging up at a normal rate. Okay, now like I told you, I said when a capacitor is fully charged, the voltage across it is maximum and its current is zero. When an inductor is fully discharged, well, its voltage is zero, or its voltage on its own would be zero, but its current would be zero. But again, the indication to remember is that when an inductor has zero, once it's fully discharged, and is sitting there idle, basically, it has zero voltage across it and no current flowing through it. And it's the current that determines how much, energy is in the system, whereas the capacitor, it's the voltage that determines how much energy is in the system. It's 1/2, CV squared for a capacitor versus, 1/2 Li squared for an inductor. That's the energy, in either of those components. But basically, what you see here is you see an inductor discharging. Its current is dropping to zero, and here, when it hits zero, it's fully discharged. But by the same token, a capacitor's current is also zero when it's fully charged. But right here, this voltage you see here is the actual voltage technically across the capacitor, but also across the inductor too. Because remember what I said when an inductor is discharging, it will generate whatever voltage it takes to try to keep that current from falling further. Okay, whereas the capacitor is eating up that energy, but its voltage is increasing. So what does the inductor have to do to maintain that? It has to generate a slightly infinitesimally higher voltage across the capacitor than the capacitor would naturally be at. So what's happening is the capacitor is charging up because it's eating current from the inductor. Alright, and the inductor is slowly losing energy, but right even down to the last little microjoule of energy it has in it, it is generating a higher voltage than the capacitor itself has on it. But again, it's infinitesimally small because these are real ideal components. So because of that, though, I mean, if this capacitor has like 9.0 volts across it, the inductor has 9.0001 volts across it, just so that it can try to maintain that current. It will generate whatever voltage is necessary to try to continue, to try to maintain that current level. But because it can't do that, it's losing energy. It can't maintain that current level forever. That's why the current keeps dropping and dropping and dropping. It's trying to battle, it's fighting a war against losing its energy. It wants that current to keep flowing because that's what gives its magnetic field life. But as its field collapses, it's having to generate a voltage that's higher and higher and higher as this capacitor eats that energy and it charges up. Okay, well, it needs, a charging capacitor, if it's going to accept more energy, needs a higher voltage across it continuously. So this inductor will supply just the amount of voltage it needs for that capacitor to eat its energy as it's trying to struggle against losing energy. But the irony is by behaving that way, it's actually transferring its energy from itself to the capacitor. And that's the thing that always used to confuse me is, okay, well, capacitors, they got a bigger voltage across them. Well, how's that? I mean, isn't it gotta, like try to transfer it to the inductor? No, because the inductor is fighting. The capacitor is not losing energy at all. Its energy is increasing. And the reason it does that is because this damn inductor keeps generating a slightly higher voltage across the capacitor. As long as the inductor has life in it, in other words, energy, it will generate a slightly higher voltage across it than the capacitor has in an effort to try to maintain its current. Remember, it's fighting for its life here, but now it's dead. It's got zero energy in it, and the capacitor has all that energy in it. But now the inductor's voltage, basically is it's not generating any voltage anymore. It's fully out of energy, and it will generate energy right up until it hits zero on the current. At that point, that voltage, that neat little voltage field, will disappear. If we took the capacitor out of this situation, you would see 0 volts on this circuit, just like we had earlier, except there's no current in the inductor anymore, so the system would be flatlined. But now the capacitor, since it doesn't have an impressed voltage, because the inductor is not generating any voltage anymore, it doesn't have an impressed voltage across it anymore. Now it's king. Okay, now it has all the energy in the circuit. Now it's boss. So basically, you got a capacitor there, but guess what? It's got this inductor that's a load there, and it's the source of voltage now. So guess what? It's almost like it was back here when I first flipped this switch, when the voltage was all of a sudden peak. Okay, now the inductor has a voltage across it, because remember, inductors will do that. They'll instantaneously generate a voltage that opposes a change in current. Because even though it's got 0 current, the inductor wants to keep it that way. So what it does is it immediately, once that capacitor becomes king, it immediately generates a field, basically equal and opposite. And you can think of it like the field was continuous all the time, even though technically it's kind of flipped. So again, the inductor technically doesn't generate a voltage field anymore now that it's out of energy, but given the fact, the capacitor's got all the energy, well, it's applying its voltage across the inductor, which is causing the inductor to counter that with its own voltage. So what you can think of it as is that, remember I said in this stage, the inductor is generating an infinitesimally larger voltage across it than the capacitor has in it. Well, here, just the opposite. It's generating an infinitesimally smaller voltage across it than the capacitor has, because the capacitor is now the source of quote-unquote voltage. The inductor is trying to resist that because it's trying to maintain its current at 0, and it's resisting the current increasing. But again, it can't do that forever. The capacitor wants to discharge, so it's actually impressing a voltage across it, just like it did when this was first charging up. And like I showed you earlier, and how these inductors charge up. The inductor immediately starts generating a voltage across it slightly less than the capacitor, so the capacitor can discharge. But because of the fact that the inductor is resisting it, well, that controls the rate of the discharge. So, this voltage across the capacitor is slowly draining off now as it, charges the current into the inductor, because the current's going negative now, so it's charging up the opposite way. Whereas, the current from the capacitor, is now positive because, again, it's flowing out of the capacitor in the direction you see right here, right now. So, in the inductor, has positive current flowing into it, just like it did to begin with. So, at that point. But any rate, like I said, right at this point, the capacitor is discharging, for this quarter cycle here. God, fuck, I hate these fucking mouse buttons. But yeah, this capacitor, is discharging, from here to here as the inductor is charging. Okay, but you can see the inductor, again, the indication of an inductor charging is its current increasing. Okay, which it does right up until here. So the inductor's current is increasing, it's just in the opposite direction. So, it's the opposite direction of what you see here. It's flowing this way, basically. So, that's why you have positive current flowing into the, flowing from the capacitor, but negative current flowing into the inductor. But this still the inductor charging up in reverse polarity, while the capacitor, its current, has become positive because it's actually, supplying the current to the inductor in a particular direction. Because again, the current starts out like you see it here, right here. Well, I mean, before I flip the switch, the current's flowing just like you see right here. All right, and it keeps doing that right up until it has zero currents flowing in the exact direction you see here. But now that I flip the switch, it's starting to charge up the capacitor, which is a negative direction. The current's flowing this from right to left here, as you can see, instead of from left to right. So that's why the capacitive current is negative at the get-go and positive for the inductor. But now right down here, the case is flipped, which means the current's flowing in the opposite direction that you see here. So the current's flowing from the inductor into the capacitor from here to here. Alright, but basically the inductor, is charging up in reverse polarity. And you can see the voltage right here peaks, once it's fully charged up, and then the cycle starts all over again, because at this point, you've got, basically a charged up inductor, but it's got the reverse polarity potential, but now it's negative 10 amps that's flowing through the inductor, but the voltage is zero, okay, right here. So since the voltage is zero, the inductor is charged up. Alright, the capacitor is discharged. Okay, but at that point, from that point on, now the inductor's in charge again, and it's going to start supplying energy into the capacitor again. The whole time it's resisting change. So now you got the current flowing more like you see here, except that the polarities are reversed now. So, but basically, you have the current discharging out of the inductor because it's moving towards zero, where at the same time, the voltage is increasing across the LC tank, as the capacitor's voltage starts to charge up. Okay, and again, that means the inductor is generating a slightly higher voltage than the capacitor has on it because it's losing energy, out of itself while it's trying to transfer it to the capacitor. Okay, and then once it hits this zero current point, that means the inductor's flat dead and the capacitor's in charge again. So, because its current zero, but its voltage is maximum. So when you see this voltage maximum, that pretty much means that, now it's time for the capacitor to take charge again, and, well, that's basically what happens. Alright, I'll flip over to this other circuit now, and like I said, this is why I'm not running this. They're lucky how this turned out here, even though I could probably try to do this manually or whatnot, but it's just clearer. See, if you go in stupid fall stat and you actually try to set these scales manually, what happens is your neutral line disappears. So that's why I did it this way. I mean, if I were to go, go properties and, set my vertical scale to something other than auto, if I set it to manual, this gray line here, this neutral line, will disappear. Okay, so it makes it harder to see, but it was actually screwing around with this is the reason I got lucky and had this turn out this way. So that's why I just kind of left it here and hadn't been running it or anything, so I could demonstrate this more clearly, because here the voltage waveform really stands out, so you can, it's easier to see that this is the voltage waveform because it's so much bigger than the two current waveforms, and you can readily see that the two current waveforms are 180 degrees out of phase with each other. So, but they're all relative, to the phase of the voltage. So, so like right here, all right, you got a current waveform for the inductor, right? Well, that's where it's at, but you can see where the voltage waveform is, which is right here. So this inductor is like positive 90 degrees shifted from the voltage, and the capacitor current waveform is minus 90 degrees with respect to the voltage, but they're 180 degrees out of phase with each other. So, but the voltages in this case, since it's a tank circuit, are both in phase with each other. Okay, so but basically, you see the currents, the voltages are in phase in a parallel LC circuit, right? But the currents are 180 degrees out of phase. Now in a series LC circuit, which is what you have here, the current, is in phase, but the two voltages are actually 180 degrees out of phase. So you get two different voltage waveforms across each component. So basically, again, in our parallel LC circuit, you can see the current, there's two different current waveforms. The capacitor's current waveform is 180 degrees shifted from the inductor's waveforms, and both of them are 90 degrees shifted from the common voltage waveform, because again, they have the same voltage across them, but they each have two different currents that are 180 degrees out of phase with each other. And if you go to an LC circuit, which I had to create a modified circuit to show you the principle of a series resonant LC circuit, because I actually had to apply a frequency source. Its resonant frequency is like 15.92 hertz, and what you see here is about 15 hertz. That's what I ran this at, so it's very close to resonance. But anyway, you can see, they have a common current waveform, but they have two separate voltage waveforms now, because the voltage waveforms are out of phase with the current waveform. So, because that's our current waveform, but one of them is, plus 90 degrees and the other is minus 90 degrees. But so the current waveforms here, there are two separate voltage waveforms here, and they're 180 degrees out of phase with each other, but 90 degrees with respect to the common current. It's a series circuit, so so they both have, since it's a series circuit, they both have the same current flowing through them, but they were free to have separate voltages across each component. And that's what you see here. You see two separate voltage waveforms, with a common current waveform. And you can, see here's the settings, at 15.92 hertz and 10 volts. But again, you can see how everything kind of builds up here, in a series resonant circuit. But I really can't, because I kind of sort of tried doing that over here with DC, but you really can't see any kind of response, because these can't actually oscillate, I was trying to take a resistor and see if I could maybe, disconnect the switch and make it oscillate, but it just doesn't quite work right. not really that surprising, but you know, I thought it was worth a try for shits and giggles. But at any rate, you know, but that's the difference between a series and a parallel circuit. You know, again, a parallel tank circuit, you know, it can have two current waveforms, separate waveforms for each component that are 180 degrees out of phase with each other, but they're all, you know, 90 degrees out of phase with reference to the voltage, whereas a series resonant circuit, or, you know, which is, you know, basically at resonance, you know, the current and voltage waveforms, you know, it'll have a common current waveform, but the voltage waveforms will be 90 degrees. And it doesn't matter if it's at resonance or not. I mean, you know, any kind of series LC circuit is going to have that. It's just right now the voltages are approximately equal because it's at resonance and they're the same kind of component character. So again, if one of these was like 1 microfarad and this was 10 millihenry, you'd see something totally different. But since these are both 10 by 10, you know, 10 millifarads and 10 millihenries, you know, everything looks, you know, like you might expect it to. But again, you get two voltage waveforms, but the current waveforms are, you know, in phase. So, you know, they're series components, so they got to have the same current going through them, but they can have separate voltages, just like the parallel. They got to have the same voltage across them because they're in parallel, but they can have two separate currents. So, and you know, it might be interesting to see what happens. Yeah, you know, I reran it but I changed it to 100 millifarad versus 10 millihenry. And they're no longer at resonance, you know, because that's going to be a different resonant frequency, but you can see that the phase relations are still maintained. You know, because basically, you know, here's the current, okay, they still have a common current waveform, but here's the voltage across the capacitor, which is way lower, but still 180 degrees out of phase for the voltage across the inductor. But they're still, you know, 180 degrees out of phase with each other and 90 degrees out of phase with the voltage. So it doesn't matter they're different values, it's just the voltage levels are going to look different. You know, that's why I like, you know, using the same component value for each, because the voltage values will look different. I mean, it would look, you know, be different too on the tank circuit, except the current values would be different instead of being pretty much identical mirror copies of each other, and that makes it easier to see. You know, here it's harder to see the voltage, the fact that the voltage waveforms are in phase with each other. So, and just ignore this, I'm not even dicking with this. It's kind of set up the same, you know, you got your little current thing, and you got the voltage you're measuring across it. So, but that's really not important to this. I could just erase all that stuff. But like I said, I'm going to go ahead and change this back. And then rerun it. Okay, so you can see now, you know, the two voltage waveforms are equal and opposite magnitude. So, because now they're at resonance again too, that helps, because, you know, how I had it before, you know, if I would have adjusted the resonant frequency, you know, which I can go ahead and change that back for you if you're curious. So 100 millifarad, but let's calculate real quickly you know, what the new resonant frequency would be. It's 1 divided by, you know, 6.28, which is 2 pi, times radical 0.1 times 0.01 for the component values. So that would be about 5.03 hertz. So if I go adjust our source, but let me reset and rerun it so you can see where we left off here. You know, the differences, you know, because that's a little voltage, that's a big voltage, and then there's the current waveform. But let me change this to 5 hertz. I don't know if the 0.03 is going to be that big of a difference, but well, wait a minute. Okay, so let's reset it and run it at resonant frequency. Okay, so if you're running at resonance, you know, even though the capacitor values are different, you know, you can still see that, you know, see here's the current waveform. Not really sure why. Probably because we haven't run it enough. Damn it. Okay. Now that I've run it enough cycles, you can see that, you know, here's the voltage waveform and of the two components, and in fact they are pretty much mirror images even though the values are different. So you know, you really don't see a different value at resonance, obviously, because these things can't be at resonance. Because at resonance, these, you know, in a series LC circuit, the reactances cancel out, basically. So, you know, so at resonance, the only thing you would see in that circuit if you had a resistor in it would be the resistance. But, you know, and right now that resistance is 1 ohm. That's why we see a 10 amp, you know, current flowing through this. It peaks at 10 amp because that's the only thing you see, because the two, you know, reactances cancel out. So, so yeah, it looks the same, you know, with the even if the component values aren't the same, it just really affects the frequency. So I just wanted to make sure, because I wasn't quite sure how that would look on the simulator. But yeah, so we can, you know, run this thing with different component values, and you see, since it's off resonant, you know, the phases are the same, but the voltages aren't. You know, they're unusual. See, with the parallel resonant circuit, I'm not doing this as an AC circuit, so, you know, I just wanted to eliminate as many variables as I could. But like I said, let me adjust the frequency back to the 15.92. So you can see how everything's, you know, equal in magnitude, and, you know, like I said, here it's harder, you know, again, we get this big montage of waveforms, unlike what it was when I originally did this, you know, because it was nice having the current waveform bigger than the two voltage waveforms so you could see it more clearly. But anyway, but these are your two voltage waveforms, and there's the current waveform. So okay, and this is the link, you know, to that circuit, by this circuit, by the way. Okay, created another one here, because I want to explore something else with you real quick, if I can get to it in a way that'll make it work. Okay, and while we're on the subject, I wanted to show you something interesting about resonant circuits, series resonant circuits too, and that's their ability to generate high voltages. Let's see here. But anyway, yeah, you can see that, you know, this is generating, you know, up to 3 kilovolts right now, and it's not done yet. You know, I need to make some adjustments here in a few minutes so that you can actually see the frequencies and everything that's going on, because this is set to 1 kilohertz right here, and then I've adjusted the values to where this is all in resonance. Because if I can remember correctly, I think that's where you get maximum. I think that's where this effect maximizes for both components, is at resonance, because they're going to be equal and opposite voltages for the you know, for the current involved. Which will eventually fall to. Let's get this going though. So you can see, you know, this will peak out at a certain value with these values I've chosen. But with a series resonant circuit, you got to remember that's like the minimum condition. That's with a series resonant circuit, you know, the capacitive reactance cancels the inductive reactance, so all you're left with is the resistance. So, which, you know, like I said, this is still just a 10 volt source here, but that's 10 volts peak. So, you know, again, the RMS value is going to be considerably less than that. You know, really should be about 7 volts. Should be 70% of that. But, well, actually, yeah, it should be 70% of peak. But anyway, that's, you know, while we got current flowing through it constantly, but in a parallel resonant circuit, if I were to put the tank in here, it would actually, you wouldn't see any current flowing through it, because that would be at maximum, you know, resonance is when it's at maximum resistance. So, you know, basically no current would actually be able to get through. But here, this is, you know, gives you maximum conduction, because, you know, they're at resonance and is a series resonant circuit. But, you know, you can see the voltage here. It's actually hard to see, but again, it's, you know, peaking out at about, you know, 10 kilovolts or so. So, you know, as it's measured there. But again, it's actually higher than that. Again, it's hard to see right now with the waveforms being like they are, with all scrunched together like this. So, but let me go in and, you know, try to change the frequencies here so you can kind of see what's going on better. Running to do it. I guess I can do the same thing here. Piece of crap. Okay. So the sim speed down and nothing here. But at any rate, it's about 12 kilovolts. You know, you can see the current peaks at about 5 amps. You know, as you can see here, and that's 90 degrees out of phase with our capacitive voltage. You know, so our voltage is lagging the current, and then, you know, the inductive voltage is leading the current. So, which is what you would expect, because with inductors, the current lags the applied voltage by 90 degrees. With a capacitor, the current leads the voltage by 90 degrees. But at any rate, you can see there's a peaking out at 11 kilovolts or so. But yet the voltage across it, is really not necessarily that high. Let's see. You can see, the overall voltage across it isn't that high. It's only like about 8 volts or something like that. So let's see if I can find it here. I don't even know if it's on this plot. Because see, this is registering 10 kilovolts because that reading is that voltage reading on this is coming from that one place. Okay, this is giving us a flat line voltage. So, it's that blue line down the middle of it. It's saying there's basically effectively no voltage across it at all. So, and that's because we're at resonance. In other words, in theory, all the voltage is probably across the resistor here on average, but not continuously, because there is a voltage there, and and again it's peaking out like 10 point something kilovolts. So across any given component, then the capacitor's got 10 kilovolts across it, and the inductor's got 10 kilovolts across it, but they're 180 degrees out of phase. Okay, I've altered some of the values here because I want it to match the calculations. I was kind of wondering why they were off. It's because I didn't have my source set right. So I went ahead and changed the source from 10 volts to 100 volts, and again it's at 1 kilohertz frequency. With the values you see here, and I chose these values, so that I could show you the math behind it. But basically, you see now we're up to about 19 kilovolts, so which is where I calculated it should be, with about a 10 amp current. I upped the resistance to 10 ohms from 1 ohm, just again to demonstrate it. Before it was at 1 ohm and we were getting like 10 or 11 kilovolts, but now we're getting about 20 with the settings I have here. But this is why I use those, because you can kind of read my little note here, because what I'm saying is that this all stemmed from a little problem I was working involving this part of this circuit. I noted that was a series resonant circuit, so I was like, okay, we're given 200 ohms and 560 ohms, so I was like, well, I wonder what would happen if that was at resonance, because I know at resonance the reactances have got to equal each other, to cancel out, because they're 90 degrees out of phase with the voltage, and therefore 180 degrees out of phase with each other. And they cancel, just like you can kind of see the maths over here implying. At any rate, so I was dicking around with the thing, and I just, was kind of curious about it, because even though I'm not to that point in the book yet, I just wanted to see, because I'm going through and just studying this basic crap to kind of refresh my memory from like, decades ago. But a lot of the stuff I actually poorly understood, so, it's possible to get good grades even though you don't really understand the material. You just know how to work math problems, But at any rate, so I set up this example, where I apply a voltage source of E of 100 volts, because because again, if you look at the problem, the book, just specifies them as impedances. They're not telling you what the the values, the resistor values and the capacitor values, or even the frequency. It's just saying 100 volts at 0-degree phase angle. So they're just keeping it simple and not messing with the formalities. But I decided to look, but I still started out with that premise. I started out, just by looking at the reactances themselves. So that's why I put 2,000 ohms for the inductive and 2,000 ohms for the reactive, set R1 to 10 volts, to 10 ohms, and then our source to 100 volts, which is exactly what you see here. And by the way, this math program is called PTC MathCAD, and this is the free version of it, so you can go get this and perform these calculations. It's a little cumbersome, but still, it works pretty well. Believe me, you're not going to get the paid version, since they only sell freaking rentware, try to charge you $700 a year for it. This used to only be like a $300 program back when software companies actually sold software. In fact, I've got the old version of it too. It just can't do the math as well. It can't handle complex complex, going back and forth between polar and complex numbers very well. But this is like MathCAD 2000. But that's a professional copy that I bought, and I've used for years, and it can do a lot of stuff, but it's not quite up to this level. They made a lot of improvements in the last 20-something years. But yeah, anyway, I'm starting out with this, these reactances, and I calculate the inductance, which is, the impedance, which is, all these things summed together, and basically it ends up being just 10 ohms, because the reactances cancel out because they're equal and opposite. So, but again, in screwing around with this stuff, I was just curious about the voltage. Even though that wasn't part of the question they asked you, I was curious about the voltage, because I remember from my past, that in a series resonant circuit, these things can generate high voltages across them. I'm always interested in high voltages. But here I calculate the total current going through the series circuit. Again, this is exactly the circuit I pretty much have drawn here. So, I calculate the current going through it, and then I calculate the voltage across the inductor, and the voltage across the resistor, and the voltage across the capacitor. And you can see it comes out 20 kilovolts, minus 90 degrees, 20 kilovolts plus 90 degrees, and then 100 volts, because we're applying 100 volts across it. Now, of course, if I wanted to simulate it, I needed to know what those values would be. So, I went and did the maths over here. I set my XL, which, I can actually just use these complex values directly, and it produces the same results, surprisingly enough. It actually drops the complex part of it, surprisingly. But anyway, I just went ahead and just, did this as, instead of using these values, which are complex, I wanted to just use these values to real, just to make sure there's nothing weird going on. But here's the capacitive value for a given frequency. It's at 1 kilohertz, and with this reactance, so that gives us about 79 nanofards for the capacitance and about 318 millifards for the inductance. So, and you can see the result of that here. So, we got, damn near 20 kilovolts, 19.31 kilovolts. And you can see the currents, about 10 amps, which is, what my calculation showed here, 10 amps. So, now you're supposed to be able to work with units in this stuff, but given the fact we're dealing with complex numbers, I haven't figured out how to work that yet. And since this is the free version of MathCAD, I don't know. So, I don't know if it can do that very readily anyway. I haven't had good success applying units yet. But at any rate, that's just very interesting. And like I said, I drew that conclusion because I always wondered what was required to generate the high voltages in a series resonant circuit. And then when I was doing this problem, I had the epiphany, oh, well, it's the amount of current. So if you got, it's the amount of current you have flowing through it versus the actual reactance of the two components. And again, at resonance, they have to have the same value, but if I chose a different frequency, they wouldn't, but one would have a different voltage across it than the other, which I can demonstrate here real quick, just by cutting those down to like 100 hertz, or, well, let's cut it down to, like 800 hertz, and then we'll speed it up. Okay, so that reduced the values quite a bit. So, but remember, we're still powering this from a 100-volt source. But this capacitor has 200 volts across it, but the inductor has minus 174 volts across it. So the voltages come way down, but we're not at resonance anymore. But that's what I've always read, and heard, that at resonance the voltage can get really high, and they can blow out your inductors and short circuit your capacitors and everything if you're not careful and choose your components right. I was always interested in it as a way of generating high voltages, but again, just like I was talking about earlier in the video, you got to make sure your capacitors are really high voltage and your inductors are really high voltage, to make that work. Because again, otherwise you're going to be shorting the coils and blowing holes in your dielectrics and your capacitors and everything else. So I mean, as you approach resonance, though, that voltage gets a much, more severe, but they're also not necessarily identical. But say one's at 270 volts and the other's at 170. So I mean, they're not the same level, but they're both still pretty high voltages. But since these capacitive values are different, but that's the only way you can make a resonant circuit, is that, you're looking for the reactances to essentially be equal, but that doesn't mean that the capacitor and inductors have the same value like we're dealing with on this tank circuit, so, but at any rate, I just thought that was an interesting, while we're discussing phases and everything, because you can still see, that everything's still in phase. This voltage is still in phase with that voltage, and they're still both 90 degrees out of phase with the current. So, but at any rate, I think that's probably saying enough about the subject.